What lies beyond our universe? Here's a challenge. Try to imagine infinite space. Picture yourself looking up at a starlit sky, with every point stretching endlessly outward. Now, imagine space curving back on itself like the surface of a sphere, finite yet without edges. Both concepts resist our natural visualization abilities, revealing cognitive limitations shared by even the brightest scientific minds. In this documentary, we're pushing the boundaries of human understanding through stunning 4K visualizations. We'll transform abstract mathematical theories like loop quantum gravity, string theory, and the multiverse hypothesis into accessible imagery, offering you a glimpse into realms previously reserved for theoretical equations and thought experiments. The boundaries of observation. Imagine standing on a beach, looking out at the horizon. You know there's more ocean beyond what you can see, but your vision has limits. The universe works the same way. We can only observe a finite portion of what might be an infinite cosmos. Our observable universe extends precisely 46.5 billion light years in every direction from Earth. This number represents the cosmic horizon of our potential observation, everything that could theoretically be detected from our vantage point since the beginning of time. This 46.5 billion light-year radius often confuses astronomy enthusiasts. The universe is only 13.8 billion years old. So how can we possibly see something more than 13.8 billion light-years away? The answer lies in cosmic expansion. While light from distant objects has been traveling for at most 13.8 billion years, the space between us and those objects has been stretching continuously during that journey. The most distant light we can detect left its source when that source was much closer to us than it is now. Think of the universe as an expanding balloon with ants on its surface. Two ants might start an inch apart, and one sends a signal toward the other. As the balloon inflates while the signal travels, by the time it reaches the second ant, they could be several inches apart, though the signal only traveled what was originally 1 inch. The cosmic horizon represents a fundamental barrier to direct observation. This limitation isn't technological. No matter how powerful our telescopes become, they cannot detect what lies beyond this threshold. Light from objects beyond the cosmic horizon simply hasn't had enough time to reach us since the universe began. While our observable universe grows larger as time passes, as light from increasingly distant regions finally reaches us, some galaxies we can see today will eventually disappear from view. The universe's expansion is accelerating, driven by dark energy. Galaxies sufficiently far from us are receding faster than the speed of light due to expanding space itself, which means their light will never reach us again once the photons currently on their way have arrived. Within our current observable sphere exists approximately 2 trillion galaxies. Each contains billions of stars, possibly trillions in larger specimens. The Milky Way alone houses between 100 to 400 billion stars, with recent research suggesting it may contain up to 1 trillion. Astronomers suspect this vast collection represents a minuscule fraction of what exists beyond our cosmic horizon. Modern observatories like the James Webb Space Telescope can peer almost to the edge of this boundary, capturing light from galaxies as they appeared just a few 100 million years after the Big Bang. These technological marvels let us glimpse the universe's infancy, but they operate within the same constraint. They cannot see beyond our cosmic horizon. This edge of our observable universe isn't a physical boundary like a cliff edge. There's no wall, no barrier, no dramatic change in the universe's properties at this distance. It's a limit imposed by the finite age of the universe combined with the speed of light. If the universe were infinitely old, our observable region would be infinitely large. But since the cosmos has a beginning, our observation has a boundary. This boundary creates a relationship between distance and time in astronomy. As we look deeper into space, we're simultaneously looking farther back in time. Light from nearby Proxima Centauri shows us this star as it was 4.3 years ago. Light from Andromeda reveals this galaxy as it existed 2.5 million years in the past. The most distant detectable galaxies appear to us as they were billions of years ago, primitive cosmic structures in the universe's youth. Our image of the universe becomes progressively more outdated as we look farther away. The most distant observable galaxies may no longer exist in the forms we see them. They had billions of years to merge, evolve, or be torn apart by cosmic processes while their ancient light journeyed toward Earth. The expansion of space complicates this picture. Objects whose light we detect from billions of years ago were substantially closer to us when they emitted that light than their current physical positions. The 46.5 billion light year radius represents how far away these objects are now, accounting for all the expansion that's occurred during light's journey. Consider the cosmic microwave background radiation, the oldest light in the universe, released about 380,000 years after the Big Bang. This radiation comes from every direction, forming the most distant observable surface in our cosmic vision. The sources of this radiation were relatively close when they emitted this light, about 42 million light years away. However, those same regions have now been carried approximately 46.5 billion light years away by cosmic expansion. The 46.5 billion light year radius helps us understand why the universe appears remarkably uniform on large scales, despite regions on opposite sides of our observable universe having never been in causal contact with each other. This horizon problem became one motivation for cosmic inflation theory, which suggests the universe expanded exponentially in its first fraction of a second, allowing regions that now appear disconnected to have once been close enough to establish equilibrium. Each observer in the universe has their own unique observable bubble centered on their position. An alien in a galaxy 10 billion light years from Earth would see a completely different set of galaxies at their cosmic horizon than we do at ours. Their observable universe would contain many galaxies forever invisible to us, while missing many that we can see. This concept of observer-dependent cosmic horizons reinforces a profound truth. The universe doesn't have a center in the conventional sense. Every point can be considered the center of its own observable universe, with space stretching in all directions around it. The 46.5 billion light year radius isn't measured from some privileged central point in the cosmos, but rather from any observer's location. Measuring the unmeasurable. That 46.5 billion light-year radius presents a mind-bending cosmic puzzle. How could light possibly travel more than 3 times the distance expected given the universe's age? This isn't a mathematical error. It's a profound clue to understanding space-time's dynamic nature. To grasp this apparent contradiction, we need to completely reconsider what distance means in an expanding universe. The key insight is that conventional distance calculations break down on cosmic scales. The universe's age of 13.8 billion years would suggest our observable universe extends only that far in light years. Yet astronomers confidently measure 46.5 billion light years. This discrepancy reveals a fundamental misconception about cosmic distances. Space itself is expanding. When astronomers observe ancient light from the universe's first galaxies, they're seeing objects as they appeared billions of years ago. During those billions of years, the space between those galaxies and us has been stretching continuously, like marks on a rubber band being pulled apart. The marks themselves aren't moving through the rubber, but the increasing distance between them creates greater separation. Consider a galaxy whose light has been traveling to us for 13 billion years. When that light began its journey, the galaxy was much closer, perhaps only a few billion light years away. But during those 13 billion years, space expanded dramatically. By the time we receive its light, the galaxy has moved to a present-day distance of over 30 billion light years, despite its light traveling for 13 billion years. To measure this expansion precisely, astronomers rely on redshift. As light travels through expanding space, its wavelength stretches, shifting toward the red end of the spectrum, similar to how an ambulance siren drops in pitch as it moves away. The greater the redshift, the more space has expanded since that light was emitted. By analyzing the redshift of thousands of galaxies, scientists have constructed a detailed expansion map throughout cosmic history. This expansion started rapidly after the Big Bang, slowed as gravity pulled matter together, and then mysteriously began accelerating about 5 billion years ago due to dark energy. Measuring this complex expansion history required multiple innovative techniques working in concert. In the 1990s, astronomers made a breakthrough by studying type I supernovae, stellar explosions that function as standard candles with consistent peak brightness. By comparing their apparent brightness from Earth with their known intrinsic brightness, scientists calculate distances with remarkable precision. Type I supernovae provided the first clear evidence that the universe's expansion is accelerating, explains Dr. Adam Rees, who shared the 2011 Nobel Prize for this discovery. We found distant supernovae were dimmer than expected in a universe where expansion was slowing down or remaining constant. Building on these findings, scientists turned to the cosmic microwave background radiation. Its tiny temperature fluctuations create acoustic peaks, regions where primordial sound waves compressed the early universe's matter. The size and spacing of these peaks reveal critical information about cosmic geometry and expansion history. These measurements were further refined with baryon acoustic oscillations, BAO, massive sound waves that traveled through the early universe's hot plasma before freezing into place. These oscillations created a characteristic pattern in galaxy distribution, with slightly more galaxies separated by about 500 million light-years. By measuring this pattern at different cosmic epochs, astronomers track how space has stretched over billions of years. The mathematical framework for understanding this expansion comes from Einstein's general relativity and the Friedmann equations derived in the 1920s. These equations allow cosmologists to work backward from current observations, reconstructing the universe's entire expansion history with remarkable precision, arriving at the 46.5 billion light-year radius. What strengthens scientists' confidence is how these independent measurement techniques, supernovae, cosmic microwave background, and baryon acoustic oscillations, converge on the same expansion history. Together, they form the consensus Lambda-CDM model, which precisely defines the universe's composition. About 68% dark energy, 27% dark matter, and 5% ordinary matter. This model enables astronomers to calculate our observable universe's radius without ever directly seeing its boundaries. The calculation considers not just the universe's age, but also the changing rate of expansion throughout cosmic history. The result, 46.5 billion light-years, represents one of humanity's most remarkable measuring achievements. This measurement continues to evolve as the universe expands. Our observable bubble grows too, not because we can see farther, but because space itself is stretching. Yet counterintuitively, many currently visible galaxies will eventually disappear from view. The accelerating expansion means light from these extremely distant galaxies will never reach us again. They're being carried away faster than their light can travel toward us. This raises profound questions. What lies beyond our observable universe? Are there regions of space we'll never be able to detect? How does this expansion ultimately determine the fate of cosmic structures? These questions highlight how measuring cosmic distances isn't just about defining boundaries. It's about understanding fundamental limits of knowledge in an expanding universe. We're not limited by our instrument's power, but by the physics of an expanding universe. Even with telescopes millions of times more powerful than James Webb, we could never see beyond our cosmic horizon because light from those regions simply hasn't had time to reach us yet. The cosmic microwave background, our ultimate visual barrier. While we've measured the radius of our observable universe with remarkable precision, there's a moment in cosmic history where all direct observation hits an absolute wall. Imagine traveling back in time, watching galaxies grow younger, stars being born, and eventually reaching a point where there are no galaxies or stars at all, just a luminous fog permeating all of space. This luminous barrier represents the ultimate limit to human perception, a literal wall of light surrounding us in all directions that no technology, no matter how advanced, can penetrate. This boundary serves as a fundamental feature of cosmic physics, not merely an instrumental limitation. When astronomers capture the faint microwave signals of the cosmic microwave background, CMB, they're detecting actual photons created at the moment the universe first became transparent, before electrons combined with protons to form neutral hydrogen atoms. The universe existed as an opaque plasma where light particles couldn't travel freely. Any photon emitted would immediately interact with the surrounding charged particles, similar to how light struggles to penetrate dense fog on a mountain road. The temperature at this critical juncture was approximately 3,000 Kelvin, about 2,700 degrees Celsius, hot enough to keep atoms ionized, but finally cool enough for electrons and protons to bind together. This process, known as recombination, happened relatively quickly by cosmic standards, transforming the universe from completely opaque to transparent over a period of roughly 100,000 years. As electrons combined with protons, photons that had been bouncing around since the earliest moments could finally stream freely through space. The CMB's extraordinary uniformity stands out. Its temperature is astonishingly consistent in all directions, approximately 2.7 Kelvin, minus 270.45 degrees Celsius, just barely above absolute zero. This consistency presents a puzzle. How could regions of the early universe that had never been in causal contact with each other reach the same temperature? This horizon problem helped motivate the theory of cosmic inflation while demonstrating the remarkable equilibrium of the early universe. Space-based observatories have mapped this cosmic wallpaper in exquisite detail. The Wilkinson Microwave Anisotropy Probe, WMAP, operated from 2001 to 2010, while the European Space Agency's Planck mission gathered data from 2009 to 2013. These satellites measured temperature variations as small as 1 part in 100,000, like detecting a grain of sand on a perfectly smooth beach stretching for miles. These tiny temperature fluctuations, visualized as slightly warmer, red, or cooler, blue, patches in CMB maps, are the embryonic seed from which all cosmic structure eventually grew. The slightly denser regions had stronger gravitational pull, gradually accumulating more matter and eventually forming the first stars and galaxies. These temperature variations reveal quantum fluctuations from the earliest moments of the universe, stretched to cosmic scales by inflation and frozen into the pattern we observe today. Dr. David Spergel, theoretical astrophysicist and former lead scientist on the WMAP mission who pioneered key techniques for analyzing these patterns, explains, "The CMB is a gold mine for cosmologists. The detailed pattern of hot and cold spots tells us about the composition and geometry of the universe, its age, and even its ultimate fate. Can we observe anything from earlier than 380,000 years after the Big Bang? While electromagnetic radiation cannot penetrate this barrier, other cosmic messengers potentially could. Neutrinos, nearly massless particles that rarely interact with matter, decoupled from the primordial plasma when the universe was just 1 second old. A theoretical cosmic neutrino background surrounds us, but these particles interact so weakly with matter that they remain beyond our current detection capabilities. Gravitational waves offer another window into earlier epochs. These ripples in space-time could carry information from the inflationary period that may have occurred in the first fraction of a second after the Big Bang. Advanced detectors like LIGO and the planned space-based LISA might eventually detect these primordial gravitational waves, offering glimpses beyond the CMB boundary. Even these alternative messengers have limits. The universe becomes increasingly dense and energetic as we approach the Big Bang, eventually reaching conditions where our physical theories break down. At the Planck time, approximately 10 to the power of negative 43 seconds after the beginning, quantum gravitational effects become significant, and our current models fail us completely. Between the Planck time and the CMB photon release stretches a vast period called the Cosmic Dark Ages. Not because it was dark, it was intensely bright, but because these eras remain largely hidden from direct observation. Analysis of the CMB's patterns confirmed that ordinary matter, the stuff of stars, planets, and people, constitutes only about 5% of the universe's mass energy content. The rest consists of dark matter and dark energy, components we detect only through their gravitational effects. The CMB temperature fluctuations also reveal the universe's geometry with remarkable precision. The sizes of the hot and cold patches match exactly what we expect in a flat universe, one where parallel lines never meet, even when extended to infinity. This precise balance provides crucial evidence supporting inflationary models. Most remarkably, the CMB gives us a direct image of the universe when it was just 0.0028% of its current age. This boundary forces cosmologists to rely increasingly on theoretical models and mathematical extrapolation the further back they look. Computer simulations recreate early universe conditions, but these models involve assumptions and approximations. The luminous wall of the CMB reminds us that some aspects of cosmic history may remain perpetually beyond direct observation. A humbling testament to the limits of human perception even as we reach ever deeper into our cosmic origins. Quantum physics, peering through the cosmic veil. While the observational wall of the CMB may seem like a dead end in our cosmic exploration, what if there's a backdoor through the quantum realm? At scales smaller than atoms, particles routinely violate the classical laws of physics that govern our everyday world, appearing from nothing, existing in multiple states simultaneously, and connecting across vast distances instantaneously. This bizarre quantum behavior connects directly to our search for what exists beyond our observable universe. As physicists increasingly suspect these phenomena provide crucial insights. When we examine reality at its smallest scales, certainty dissolves into probability clouds. Particles exist as probability distributions until measured, a phenomenon called quantum superposition. This fundamental uncertainty represents a core feature of reality itself. Heisenberg's uncertainty principle mathematically demonstrates the limits of what we can know, like trying to simultaneously photograph both the position and speed of a hummingbird. The clearer one becomes, the blurrier the other grows. Applied to cosmology, this principle suggests our universe's earliest moments and outer boundaries have inherent limits to their knowability. Consider empty space from a quantum perspective. What appears as nothingness actually teems with activity. Quantum fields permeate everything like an invisible ocean, with virtual particles constantly bubbling up and disappearing like microscopic sea foam before our instruments can detect them. These aren't merely theoretical. They produce measurable effects like the Casimir force, where two uncharged plates placed extremely close together experience attraction because the waves between them are limited compared to the open sea outside. This quantum foam transforms our understanding of cosmic boundaries. If nothing within our universe buzzes with activity, then the nothing beyond might harbor entirely different quantum fields with different properties. Cosmologists propose that quantum fluctuations in these fields could spawn new universes through processes similar to those that triggered our own Big Bang. Quantum entanglement offers another window into possible cosmic connections. In laboratories across Earth, scientists have demonstrated how entangled particles form a single quantum system regardless of distance. Measure one particle, and its partner instantaneously assumes corresponding properties, what Einstein called spooky action at distance. These experiments began with photons separated by meters, but have progressively scaled to kilometers and even to space-based tests, suggesting these connections transcend our conventional understanding of space-time limits. Theoretical physicist Juan Meldicena explored similar boundary crossing through the holographic principle, suggesting our three-dimensional reality might be encoded on a two-dimensional surface, similar to how a hologram creates a 3D image from a 2D medium. This principle emerged from string theory and offers potential mechanisms for information transfer between cosmic realms. Quantum tunneling represents another boundary crossing mechanism. Unlike water requiring enough energy to climb over a dam, quantum particles can pass through seemingly impenetrable barriers with calculable probability, essentially finding shortcuts through energy landscapes. Applied to cosmology, quantum tunneling might allow interactions between universes that appear completely separated according to classical understanding. The uncertainty relationship between time and energy allows particles to briefly borrow energy from the vacuum if they return it quickly enough. Physicist Alan Guth, who developed cosmic inflation theory, suggests that quantum fluctuations during inflation could create bubble universes with varying physical constants and laws. These bubbles might form a cosmic multiverse arising from quantum principles. Each bubble universe would experience its own Big Bang and subsequent evolution, potentially with different physical constants governing its development. Quantum cosmology models apply these principles to the entire universe, treating it as one massive quantum system. Just as electrons exist in probability clouds around atomic nuclei, our universe might represent one probable state among many configurations. Hugh Everett's many-worlds interpretation suggests that all possible outcomes of quantum measurements occur in separate branches of reality, creating new universe versions with each quantum event. The vacuum energy prediction represents one of physics' greatest unsolved puzzles. Quantum field theory predicts empty space contains enormous energy from virtual particle fluctuations, far larger than observational evidence indicates. This discrepancy might indicate connections to other cosmic realms that modify vacuum energy in our observable universe. Leonard Susskind explores these concepts through the string theory landscape, suggesting our universe occupies one valley in a vast terrain of possible states. Quantum tunneling might allow transitions between these states, creating a network of connected but distinct universes with varying physical properties. Quantum loop gravity proposes that space-time itself has quantum properties, composed of discrete units at the Planck scale. In this framework, what appears as a cosmic boundary might actually be a phase transition where space-time changes state, like water transforming between liquid, solid, and gas. The iconic double-slit experiment demonstrates how particles behave as waves of probability until measured, raising questions about unobserved cosmic regions. Do these regions exist in defined states, or as clouds of quantum possibilities until brought into contact with our observable universe? While no experiment confirms quantum connections between universes, mathematical models consistently suggest this possibility. The mathematics describing quantum field fluctuations naturally produces multiple cosmic domains. Solutions to equations in string theory and quantum gravity frequently yield multiverse hypotheses, science, or speculation. Beyond mathematical abstractions lies a startling possibility that challenges our very definition of everything. If our equations naturally produce multiple universes rather than just one, where does speculation end and scientific theory begin? The multiverse hypothesis sits at this precise boundary, simultaneously the most outlandish and mathematically consistent framework for understanding reality. The multiverse concept emerges independently from several branches of modern physics. Multiple theoretical frameworks, each developed to solve different problems, converge on the same conclusion. Our universe appears to be one of many. Consider the inflationary model of the early universe, developed to explain why cosmic space appears remarkably flat and uniform. This theory proposes that in the first fraction of a second after the Big Bang, our universe underwent exponential expansion, stretching faster than light speed. Theoretical physicists discovered something unexpected about inflation. Once it starts, it naturally becomes eternal in most regions of space. Picture a cosmic foam where rapidly expanding space creates bubble universes that separate from one another. Each self-contained bubble develops its own physical laws and constants. Our entire observable cosmos exists as one bubble in this vast, ever-expanding sea of universes. Andre Linde, one of inflation's pioneers, describes it as a process that creates an infinite number of universes. This eternal inflation scenario produces what cosmologists call a multiverse level 2, where different regions may have entirely different fundamental constants and even different dimensions. Testing these ideas presents a formidable challenge. How can we verify other universes when we're confined to our own? This tension defines multiverse physics, mathematically compelling models that seem to reside beyond direct experimental confirmation. Physicists have developed potential indirect tests. One approach examines our cosmic microwave background for bubble collisions, places where a universe might have physically contacted another bubble universe. These would appear as circular patterns of temperature variations with distinctive signatures. Another approach involves examining galaxy distribution. If our universe collided with another, the resulting gravitational effects could create subtle asymmetries in how matter is distributed. Detailed sky surveys mapping billions of galaxies might eventually reveal these patterns. The quantum realm offers a different multiverse concept. Hugh Everett's many worlds interpretation suggests that every quantum event with multiple possible outcomes causes reality to branch into separate universes containing each result. When a quantum particle exists in multiple states until measured, the many worlds theory proposes all potential states actually occur in different parallel universes. This creates a multiverse level 3, where identical copies of our universe diverge with each quantum decision. This interpretation mathematically resolves quantum paradoxes without requiring the mysterious collapse of probability waves. It provides an elegant solution if you accept infinite parallel realities as the consequence. String theory provides yet another path to the multiverse. The mathematics of string theory works best in higher dimensional space and produces what physicists call the string theory landscape, a vast terrain of possible vacuum states, each representing a potential universe with different physical laws. The number of configurations in this landscape is staggering, approximately 10 to the power of 500 different possible universes. Each would have different fundamental constants, particle properties, and observable dimensions. Our universe represents just one solution among this virtually infinite set. The string theory multiverse might explain physics' most puzzling observation, the apparent fine-tuning of our fundamental constants. Values like gravity's strength, electron mass, and cosmological constant appear calibrated with extraordinary precision to allow stable atoms, stars, and life. With slightly different values, our universe would collapse immediately or expand so rapidly that no structures could form. This apparent fine-tuning has troubled physicists for decades. But in a multiverse with countless configurations, universes with every possible combination of constants naturally exist. We find ourselves in one of the rare universes where conditions happen to support observers. As physicist Leonard Susskind explains, we're just one of the bubbles in which by accident the constants of nature were suitable for the evolution of complexity in life. This transforms seemingly miraculous fine-tuning into an expected statistical outcome, an application of the anthropic principle. We observe these precise constants because they're necessary for observers like us to exist. Not all physicists embrace the multiverse concept. Critics argue these theories stretch beyond proper science. Theoretical physicist Paul Steinhardt cautions, the multiverse idea seems to be the easy way out. Instead of trying to explain the universe we see, it basically gives up on that goal. The debate centers on scientific testability. Traditional theories make predictions verifiable through observation. But multiverse theories involve phenomena potentially beyond our observational capacity. Some philosophers suggest redefining scientific evidence when dealing with concepts at observation's boundary. Statistical consistency, mathematical elegance, and explanatory power might supplement direct observation as evaluative criteria. Others propose creative testing methods. Max Tegmark suggests that in a mathematical multiverse, our universe should be typical rather than special. By identifying what makes universes typical in various models, we could test whether our universe matches these predictions. Another approach examines the cosmic microwave background for patterns indicating a cyclic universe, repeatedly collapsing and expanding, with our Big Bang being the latest in an infinite series. This would constitute a multiverse level 1, where other universes exist beyond our observable horizon with potentially identical physical laws. String theory, unveiling hidden dimensions. From the vast cosmic multiverse, we now narrow our focus to something equally profound yet infinitely small. The mathematics of string theory points to a startling possibility. Our three-dimensional experience might be just a limited perspective of a universe with far more dimensions. Dimensions that remain hidden yet shape everything we observe. At its core, string theory reimagines the fundamental building blocks of reality. Instead of viewing particles as dimensionless points in space, string theory proposes they are tiny, vibrating filaments of energy. These strings exist at scales of approximately 10 to the power of -35 meters, the Planck length, where quantum effects and gravity converge. Much like different vibration patterns on a violin string produce different musical notes, the specific vibrations of these cosmic strings determine whether they manifest as electrons, quarks, or other particles we observe. This elegant concept helps unify our understanding of the four fundamental forces: gravity, electromagnetism, and the strong and weak nuclear forces. Yet this unification comes with a remarkable mathematical requirement. For the equations to work consistently, our reality must contain extra dimensions beyond the familiar 3 spatial dimensions and one-time dimension we experience daily. Most versions of string theory require a total of 10 dimensions, 9 spatial dimensions plus time. M theory, considered by many physicists to be the mother theory that encompasses all string theories, requires 11 dimensions. This raises an obvious question. If these extra dimensions exist, why don't we perceive them? The most widely accepted explanation is that these extra dimensions are compactified, curled up into incredibly tight spaces at every point in our universe. Imagine our universe as an elaborate layered cake. We perceive and move through the large, obvious layers, but at every point, there are intricate decorative swirls too small to see with the naked eye. These hidden patterns, existing at every point in space, would represent the extra dimensions, influencing the flavor and structure of reality while remaining imperceptible to our senses. The mathematics suggests these compactified dimensions form complex geometric shapes called Calabi-Yau manifolds. The specific configuration of these hidden dimensions, their exact shapes and sizes, would determine the physics we observe in our four-dimensional experience. Different arrangements would result in different physical laws, potentially explaining why our universe has the specific properties it does. This matters because it could answer why fundamental constants like the strength of gravity or the mass of particles have the exact values needed for stars to form and life to exist. The geometry of these compactified dimensions might solve physics' most perplexing questions. Why do fundamental particles have the exact properties they do? For instance, why does an electron have precisely 1/1836 the mass of a proton? In string theory, these seemingly arbitrary values emerge naturally from the specific geometry of the hidden dimensions, similar to how the shape of a musical instrument determines which frequencies it can produce. Some string theorists propose an alternative model involving large extra dimensions. In these scenarios, our universe exists on a four-dimensional brane, short for membrane, that floats within a higher dimensional space called the bulk. Other branes might exist parallel to ours, like secret corridors running alongside the main hallway of an elaborate castle. We remain confined to our corridor, but the structure of the entire castle determines what happens within our space. Gravity presents a particularly interesting case in these models. While electromagnetic, strong, and weak forces might be confined to our brain, gravity could potentially leak into these extra dimensions. This leakage might explain why gravity appears so much weaker than the other fundamental forces. It's diffusing its strength across dimensions we cannot access. For physicists trying to unify the forces of nature, this provides a mathematical solution to a problem that has stumped scientists for decades. This brain model leads to another fascinating possibility. What we perceive as the Big Bang might actually have been a collision between two higher-dimensional brains. In this ekpyrotic scenario, our entire cosmic history would represent the aftermath of a higher-dimensional collision event. Some physicists suggest such collisions might occur repeatedly, creating cycles of universal creation and destruction. These extra dimensions remain theoretical, but scientists have proposed experimental approaches that might detect their existence. At particle accelerators like the Large Hadron Collider, certain collision patterns might reveal energy leaking into extra dimensions. As theoretical physicist Lisa Randall notes, we're trapped on our four-dimensional brain, much like a bug trapped on the surface of a pond. Our perceptual limitations prevent us from directly experiencing these dimensions, but mathematics suggests they must exist for our most comprehensive theories to work. This dimensional framework offers an intriguing explanation for dark matter as well. Some models propose that dark matter might be ordinary matter residing on a parallel brain, invisible to us except through gravitational effects that propagate between brains. This could explain why dark matter interacts gravitationally with visible matter while remaining otherwise undetectable through our instruments. String theory's extra dimensions also provide a potential resolution to the hierarchy problem, the puzzle of why gravity is so much weaker than the other fundamental forces. If gravity spreads its influence through additional spatial dimensions, while other forces remain confined to our brain, this would naturally explain the apparent weakness of gravity in our four-dimensional experience. The beyond might not be far away in conventional space. It might be perpendicular to all directions we can perceive, present at every point yet invisible to us. Loop quantum gravity, space-time reimagined. While string theory asks us to imagine invisible dimensions, a competing theory questions something far more fundamental. What if the space between you and this screen isn't continuous at all, but made of tiny, indivisible pieces like pixels on a cosmic display? This radical perspective comes from loop quantum gravity, or LQG, a theoretical framework that stands in stark contrast to string theory's approach. Rather than adding dimensions to our universe, LQG reimagines the very fabric of reality itself. According to this theory, space isn't infinitely divisible, but consists of discrete, quantum units at the incredibly tiny Planck scale. Just as a high-resolution digital photo reveals its pixel structure when zoomed in far enough, LQG proposes that what appears to be smooth, continuous space is actually composed of fundamental building blocks, atomic units of geometry that cannot be subdivided further. Space itself has a fundamental resolution limit. These indivisible units form spin networks, intricate webs of quantum relationships that define the structure of space itself. As these networks evolve through time, they create what researchers describe as a quantum foam, a bubbling, dynamic foundation of reality at its smallest scales. One profound implication concerns cosmic singularities, points where matter becomes infinitely dense and physics breaks down. Classical physics predicts such singularities must exist at the center of black holes and at the moment of the Big Bang. However, the quantized nature of space in LQG naturally prevents these infinities from occurring. This prevention of singularities leads to one of LQG's most revolutionary proposals, the Big Bounce. Rather than our universe beginning from a singular point of infinite density, LQG suggests it may have bounced from a previous contraction. Under extreme density, quantum geometric effects would generate a repulsive force, causing the universe to rebound rather than collapse completely. Carlo Rovelli, one of LQG's founding theorists, explains it clearly. The theory predicts that time continues before the Big Bang. Our universe may have emerged from a collapse of a previous universe. This bounce mechanism suggests our cosmic beginning wasn't the beginning at all, but a transition from a previous cosmic phase. There could be previous iterations of universes stretching back in cosmic time, connected through these quantum bounce events. At extreme conditions, like those found at cosmic boundaries or inside black holes, LQG suggests space-time might undergo phase transitions, similar to how water transforms to ice. These transitions represent fundamental shifts in the behavior of space itself. The atomic units of space reorganize into entirely different configurations under certain conditions. These phase transitions could serve as gateways between different cosmic regions. Physicist Abhay Ushtakar has developed models where quantum tunneling events, a phenomenon where particles can pass through seemingly impenetrable barriers, could allow connections between different universes or regions of space-time. The theory offers several potential revelations for contemporary physics puzzles. A resolution to the black hole information paradox by preserving information in quantum geometry. An explanation for our universe's remarkable flatness without requiring inflation. A fundamental limit to how precisely we can measure distances below the Planck scale. Potential connections between separate cosmic regions through quantum tunneling. Unlike string theory's requirement for additional spatial dimensions, LQG works within our familiar 4 dimensions of space-time. However, it fundamentally transforms our understanding of what those dimensions actually are. Space becomes an active, dynamic participant composed of quantum relationships rather than a passive backdrop. The quantum nature of space might explain why our cosmos is geometrically flat with incredible precision, a feature that seems suspiciously fine-tuned. LQG provides an alternative to inflation theory. Quantum geometric effects could naturally drive the universe toward flatness. The discreteness of space-time also suggests a fundamental limit to measurement precision below the Planck scale. Martin Bojewald, a prominent LQG researcher, has developed models suggesting that at cosmic boundaries, the uncertainty in space-time measurements might increase dramatically, creating a kind of quantum fog that blurs the distinction between different universes. Testing these predictions presents enormous challenges. The Planck scale is approximately 10 to the power of negative 35 meters, unimaginably smaller than anything we can directly measure. However, scientists are developing indirect tests that might reveal signatures of quantum geometry. One approach involves searching for tiny violations of Lorentz invariance, the principle that physics remains consistent regardless of an observer's speed or direction. If space has a discrete structure, light traveling across vast cosmic distances might show slight variations in speed depending on its energy, potentially measurable in gamma-ray bursts from distant galaxies. Another promising avenue involves gravitational waves, ripples in space-time created by violent cosmic events. The quantum nature of space might leave subtle imprints on these waves as they propagate across the universe. Future gravitational wave observatories with increased sensitivity might detect these quantum signatures. Perhaps the most tantalizing test comes from examining the cosmic microwave background in unprecedented detail. If our universe emerged from a quantum bounce rather than a singular Big Bang, this might leave distinctive patterns in the polarization of the CMB radiation, patterns that differ from those predicted by inflationary models. The BICEP experiment and Planck satellite have already made remarkable progress in measuring these polarization patterns, though definitive evidence for quantum gravity effects remains elusive. Dark energy and dark matter, cosmic shadows. Imagine discovering that nearly everything you thought made up reality is just a fraction of what actually exists. The universe we can see and measure accounts for merely 5% of cosmic content. The rest consists of invisible forces that might connect our universe to others beyond our comprehension. When astronomers track the movement of stars within galaxies, they find something profoundly unsettling. Stars orbit much faster than they should based on the visible mass present. Similarly, when measuring cosmic expansion, they discovered it's accelerating rather than slowing due to gravity as expected. These observations reveal our universe is primarily composed of two mysterious substances, dark matter and dark energy. Dark matter functions as an invisible scaffold supporting cosmic structure, like an unseen framework holding up a magnificent city. Though it doesn't interact with light or electromagnetic forces, its gravitational effects are unmistakable. We observe its influence in galaxy rotation curves, gravitational lensing patterns, and a large-scale structure of the universe. Without dark matter, galaxies would tear themselves apart as they rotate, lacking sufficient gravitational binding from visible matter alone. Dark energy presents an even greater enigma. It permeates space uniformly, creating a repulsive force that drives galaxies apart at an accelerating rate. The nature of this cosmic accelerator remains profoundly mysterious, yet constitutes the dominant component of our universe's energy content. These cosmic shadows become particularly intriguing when considering how they might connect to realms beyond our observable universe. The vacuum energy problem illustrates this connection, perhaps the most spectacular failure in theoretical physics. Quantum field theory predicts that empty space should seethe with energy from virtual particles popping in and out of existence. However, the calculated value exceeds observational measurements by an almost inconceivable factor, 10 to the power of 120. This discrepancy, called the cosmological constant problem, is off by more orders of magnitude than there are atoms in the observable universe. This extraordinary mismatch suggests something fundamental is missing from our understanding. One possibility is that dark energy represents an interaction with other universes or dimensions. In some theoretical frameworks, our cosmos might exist within a higher dimensional bulk space, with dark energy representing a form of leakage between dimensional boundaries. Physicist Justin Curry proposes that dark energy might result from our universe interacting with a parallel mirror universe through a form of scalar field coupling. In this scenario, the acceleration we observe emerges from this cross-dimensional interaction. Such models help explain why dark energy's strength appears finely tuned. It's determined by the relationship between multiple cosmic realms. Other theories suggest dark energy might be a dynamic field that varies across space and time rather than a static property of the vacuum. These quintessence models propose that our universe might be influenced by fields extending beyond our observable horizon, connecting regions of space-time that appear causally disconnected within conventional physics. Dark matter offers similarly intriguing connections to beyond-universe physics. While conventional explanations focus on undiscovered particles within standard model extensions, some theories propose more exotic origins. Theoretical physicist Catherine Fries has explored models where dark matter particles might occasionally interact with ordinary matter through portals to extra dimensions or parallel universes. In the brainbox scenario, dark matter could consist of ordinary matter trapped on a parallel brain membrane in higher dimensional space. While gravity can propagate between brains, other forces remain confined, explaining why dark matter exerts gravitational influence without electromagnetic interaction. This would mean dark matter is ordinary matter existing in a different dimensional location. The distribution patterns of dark matter throughout the universe might also contain clues about cosmic boundaries. Computer simulations cannot fully reproduce observed dark matter distributions using standard cosmological parameters alone. These discrepancies might indicate influences from beyond our observable horizon affecting how dark matter clumps and disperses on large scales. Consider the axis of evil, an unexpected alignment of temperature patterns in the cosmic microwave background radiation that appears oriented relative to our solar system. This alignment shouldn't exist in a standard cosmological model, but might make sense if our universe has interacted with another universe or exists within a larger cosmic structure. Some theoretical models suggest dark energy might be a consequence of our universe relaxing after interaction with another universe. Physicist Laura Mersini-Houghton proposed that quantum entanglement between universes in the multiverse could leave observable imprints on our cosmic microwave background, potentially explaining some large-scale anomalies we observe. The unusual properties of both dark matter and dark energy transform these cosmic shadows from frustrating puzzles into potential messengers from beyond our cosmic horizon. Their behavior doesn't neatly fit within established physics, suggesting connections to phenomena outside our observable universe. Recent astronomical surveys have begun mapping dark matter distribution with unprecedented precision. The Dark Energy Survey has created detailed maps showing how dark matter forms a cosmic web throughout space. Similar efforts from the Euclid Space Telescope and the upcoming Vera Rubin Observatory will further refine these maps, potentially revealing subtle patterns indicating influences from beyond our observable universe. As we'll explore in the next section, cutting-edge detection systems are being developed to directly search for these mysterious cosmic components. These sophisticated instruments may soon provide breakthrough evidence about whether dark matter and energy truly represent bridges to other universes, bringing us closer to future detection technologies on the horizon. What if scientists are developing instruments that might detect signals from beyond the supposedly impenetrable cosmic horizon? These revolutionary technologies completely reimagine how we observe the unobservable. When we discuss seeing beyond our cosmic horizon, we're not talking about conventional telescopes with bigger mirrors. The challenge requires entirely new detection paradigms that can capture indirect evidence of what might exist beyond observable reality. It's like detecting a storm beyond the horizon, not by seeing it, but by measuring subtle changes in wave patterns reaching our shore. Among the most promising approaches are next-generation gravitational wave observatories. While current detectors like LIGO and Virgo have revolutionized astronomy by detecting ripples in space-time from colliding black holes and neutron stars, they only capture relatively recent cosmic events. The planned Laser Interferometer Space Antenna, LISA, will take this technology to space, using 3 spacecraft flying in triangular formation, separated by 2.5 million kilometers, to detect much longer wavelength gravitational waves. LISA excites cosmologists with its potential sensitivity to primordial gravitational waves, ripples in space-time created during the inflation period immediately following the Big Bang. These waves would carry information from before the release of the cosmic microwave background, potentially revealing conditions that existed mere fractions of a second after the universe began. Even more ambitious is the proposed Big Bang Observer, BBO, designed specifically to detect the gravitational wave background from the early universe. By measuring the polarization patterns in these ancient waves, scientists might identify signatures of processes that preceded our Big Bang, perhaps even evidence of previous universal cycles or interactions with other cosmic domains. Quantum physics offers another avenue for detecting what lies beyond our observable universe. Researchers are pushing quantum experiments to increasingly macroscopic scales, testing whether quantum phenomena like entanglement maintain their strange properties across greater distances and with larger objects. If quantum connections truly transcend conventional space-time limitations, as some theories suggest, they might provide a window into realms beyond our cosmic horizon. Consider the quantum space telescope concept. Unlike conventional telescopes that capture electromagnetic radiation, this theoretical instrument would measure quantum correlations between particles that might reveal connections to domains beyond our observable universe. Some models suggest that quantum entanglement might connect particles across different universes or through extra dimensions, potentially allowing indirect detection of what exists beyond our cosmic boundaries. Researchers at institutions like the Institute for Quantum Optics and Quantum Information in Vienna are already performing sophisticated tests of Bell's inequality, the mathematical relationship that distinguishes quantum mechanical systems from classical ones. By extending these tests to cosmological scales, scientists hope to determine whether quantum connections could provide evidence of cosmic domains beyond our observable universe. Particle physics presents a third powerful approach to probing the cosmic unknown. While the Large Hadron Collider at CERN has transformed our understanding of fundamental particles, future accelerators might reach energies sufficient to produce phenomena predicted by theories about what exists beyond our universe. The proposed Future Circular Collider, FCC, would dwarf the LHC with a 100-kilometer circumference, potentially reaching energies up to 100 TeV, energies that haven't existed in our universe since shortly after the Big Bang. At these extreme energies, physicists might detect evidence of extra dimensions, produce microscopic black holes predicted by some string theory models, or identify particles that could serve as messengers between our universe and others. Meanwhile, astronomical surveys are achieving unprecedented precision in mapping our observable universe, potentially revealing subtle anomalies that might indicate interactions with cosmic domains beyond our horizon. The upcoming Euclid Space Telescope and the ground-based Vera-C Rubin Observatory will map billions of galaxies with extraordinary precision, creating three-dimensional maps of matter distribution throughout cosmic history. These ultra-precise maps might reveal unexpected patterns or alignments in cosmic structure that current models can't explain, potentially indicating influences from beyond our observable universe. Particularly intriguing would be evidence of non-Gaussian features in the distribution of galaxies or in the cosmic microwave background, statistical patterns that might indicate interactions with other universes during cosmic inflation. Some researchers are developing specialized instruments to search for specific signatures of multiverse interactions. The CMB S4 project will deploy multiple telescopes at the South Pole and in Chile to measure cosmic microwave background polarization with unprecedented sensitivity. These measurements could potentially detect bubble collision signatures, circular patterns in the CMB that might indicate where a universe physically contacted another during its formation. Theoretical physicist Matthew Johnson and colleagues have developed sophisticated computer simulations of what these bubble collision signatures would look like if our universe had indeed collided with others during its early expansion. By comparing these theoretical patterns with actual observations, scientists might find indirect evidence of universes beyond our own. The ultimate limitation in all these approaches remains the cosmic variance problem. With only one observable universe to study, distinguishing rare statistical fluctuations from genuine signals of beyond-horizon physics presents an enormous challenge. This has led some researchers to propose studying universes in a lab, using quantum simulators or advanced computational models to create artificial systems that mimic cosmic evolution under different physical laws. What unites all these approaches is a fundamental shift in scientific methodology when confronting cosmic boundaries. Rather than direct observation, scientists rely on mathematical consistency, indirect signatures, and statistical patterns to infer what might exist beyond our observable universe. This represents the greatest strength of scientific inquiry, the ability to develop testable predictions about phenomena that seem permanently beyond direct detection. Philosophical frontiers, redefining reality. Beyond the technical challenges of detecting other universes lies an even more profound question. If multiple universes exist, each with different physical laws, is our reality just one arbitrary possibility among countless others? This possibility expands our cosmology and completely reframes what we mean by existence. Philosophy has wrestled with questions of reality for millennia, but multiverse theories introduce unprecedented complications. When physicists propose infinite parallel universes, they challenge our most basic assumptions about what constitutes reality itself. These theories force us to reconsider whether our universe, with its particular set of physical laws, represents anything special or necessary. The philosophical implications begin with ontology, the study of what exists and how it exists. Traditional ontology assumed a single coherent reality governed by universal laws. Multiverse theories suggest instead that reality might be fundamentally plural, with our universe representing one manifestation among countless possibilities. This transforms existence from a binary state into a spectrum where different universes might exist in different ways or with varying degrees of reality. What happens to our concept of reality when it becomes merely one arrangement among infinite others? Consider our universe's apparent fine-tuning. The fundamental constants of physics, like the strength of gravity, the mass of electrons, or the strong nuclear force, appear calibrated with extraordinary precision. If any were slightly different, stars couldn't form, chemistry wouldn't work, and life, as we know it, would be impossible. This fine-tuning presents a striking coincidence that demands explanation. The traditional explanation invoked design. Some higher intelligence precisely calibrated these values to enable life. But the multiverse offers an alternative: selection bias. If infinite universes exist with every possible combination of physical laws, then universes capable of supporting observers would be rare, but inevitably, observers would only exist in those universes capable of supporting them. We find ourselves in this precisely tuned universe not because it was designed for us, but because it's the only type where we could possibly exist to ask the question. Philosopher of physics Tim Maudlin suggests this transforms our understanding of what requires explanation. In a multiverse scenario, he explains, the apparent fine-tuning of our universe is no more surprising than finding yourself on Earth rather than floating in deep space. Of course, you're on Earth. You couldn't survive anywhere else. This perspective, formalized as the anthropic principle, shifts the explanatory focus from why these specific values to why a multiverse with varying values. Yet this solution creates new philosophical challenges. Traditional scientific theories aim to be both explanatory and predictive. The anthropic reasoning within multiverse theories provides explanations but struggles with predictions. If literally anything is possible somewhere in the multiverse, do we risk creating a theory that explains everything and therefore explains nothing in particular? Philosopher Karl Popper argued that scientific theories must be falsifiable, capable of being proven wrong through observation. But how do we falsify claims about universes beyond our observation? This leads to debates about what separates legitimate science from untestable metaphysics. Multiverse theories also transform our understanding of causality. In classical physics, every effect has a specific cause that precedes it. But in quantum multiverse models, events might have causes that exist in parallel branches of reality, a radical departure from our intuitive understanding of cause and effect. Imagine reality as a cosmic kaleidoscope, where each twist reveals patterns that influence each other across dimensional boundaries. The boundary between mathematics and physical reality becomes particularly blurred in multiverse theories. Mathematical physicist Max Tegmark proposed that mathematical consistency isn't just how we describe reality, but is reality itself. In his mathematical universe hypothesis, Tegmark suggests that any mathematically consistent structure exists in the same sense our universe exists. This implies that mathematically coherent universes possess a form of existence independent of observation. This view challenges the traditional distinction between what's real and what's merely theoretical. If mathematical structures have an independent existence, then the equations describing other universes become windows into genuine realities. As physicist Eugene Wigner noted, the effectiveness of mathematics in describing our universe might be essential. Reality is fundamentally mathematical. These perspectives transform our concept of consciousness and personal identity. If infinite universes exist containing every possible variation of ourselves, what becomes of the continuous self? How does personal identity function across diverging quantum branches? The ethical implications are equally profound. If every possible decision happens in some branch of reality, what becomes of moral responsibility? Some philosophers counter that even if all possibilities occur somewhere, our decisions still determine which branch of reality we experience, preserving moral agency within our particular cosmic branch. Perhaps most fundamentally, multiverse theories challenge the relationship between science and meaning. If our universe is one arbitrary possibility among infinite others, does this diminish its significance? Philosopher Thomas Nagel suggests this might create an absurdity with a significance we find in our lives' conflicts with our cosmic insignificance. Yet others find new meaning in multiverse models. Could the existence of every possibility transform how we think about potentiality and actuality? Rather than seeing unrealized possibilities as abstractions, we might consider them as concrete realities in other cosmic domains, connecting us to a broader fabric of existence. The boundaries between physics and metaphysics blur in these discussions. Questions once considered beyond science, like why does anything exist at all, now intersect with theoretical physics, requiring scientists to engage with philosophical questions they might have previously avoided. We've journeyed from quantum scales to cosmic boundaries, from mathematical models to philosophical implications. But this exploration isn't an endpoint, it's a beginning. The frontier of our cosmic horizon represents the edge where observation ends and theoretical exploration begins. What's truly remarkable is how we've developed frameworks to conceptualize what might exist beyond our universe despite fundamental observational limitations. Our quest evolves as new instruments and theories emerge, pushing back the boundaries of the unknown. The greatest insight remains that knowledge itself expands as a dynamic frontier, growing alongside our understanding of cosmic reality. What mysteries might you help uncover in this